So the second half of my presentation is going to focus on why we have so much oil in the United States. So you just learned, and you may have known already, that the United States leads the world in oil production. It hasn't always been that way. Okay, it was at one time, and then it wasn't for a while. Now it is again. So in order to lead the world in energy production, two things are happening. One is we have the raw materials to begin with. We have the rocks that have the oil in there that we can get it out of. And secondly, we have the technology that's really helping in the last few years. So 10 years ago, 15 years ago, if you'd asked me if I would ever teach a petroleum geology course again, I'd have said no, because we're on a production decline. So things have happened, the prices went up, technology's improved, and the world's a different place. So you can't predict what the future has in store. So let's do a historical review. Let's talk about where oil comes from and how specifically the United States and Illinois happens to be blessed with petroleum resources. So if you look at the word petroleum, the oldest derivation that I could find with it is used in the 1546 scientific text by Agricola. And in those days, people liked to Latinize their names. This person was German. His name was John Bauer. But you have to, Agricola, Bauer, I think, is farmer in German. So if you Latinize yourself to make you sound fancy, Agricola is what came out. But if we look at the derivation, in Greek, petra is rock and oleum is oil, and that's where the word comes from. And if we want to look back in the one of the oldest books in the world, if you look at Genesis, and God said unto Noah, make yourself an ark of gopher wood, make rooms in the ark and cover the inside and out of it with pitch. Well, pitch is oil. So the utility of this as a substance and of use is quite historic. So you've been bombarded with terminology, and I apologize, I missed the earlier part of the morning, but I want to review some of these words because sometimes people in the game use words interchangeably that it's hard for people that aren't in the game to be able to keep up with. Okay, so you hear the terms hydrocarbons. Well, what is it? That's hydrogen and carbon, of course, but also some bits of sulfur and nitrogen and oxygen. Okay, so petroleum is not just one chemical. It's a very complex combination of a bunch of different chemicals. Not all oil is alike. If you go to the refinery tomorrow, they're going to tell you, and I guess the pipeline too, either part in the morning tomorrow is going to tell you a little bit about what the characteristics of the Illinois variant of petroleum are. So not all petroleum is alike. So if we think of the hydrocarbons, the simplest is methane, CH4. That's known as natural gas. The liquid variant is what we call crude oil, and that's what's refined into the products that we use. And some of the more plastic part would be the tar or the pitch or asphalt. And then the solid hydrocarbons would be things like coal and the precursors for oil. So we believe that oil has a biogenic origin, and the evidence for that is pretty strong. Okay, so 99% of all oil is in sedimentary rocks in sedimentary basins. So we have the Illinois Basin. Joan talked about that earlier today. We also have 99% of oil is in rocks younger than 500 million years old, and that's where we have an abundant fossil record. So this is a fossil fuel. We think these are associated with ancient life. We also know that what we call the source rocks, these black shales, you can heat them up and you can get oil to drip out of them. And you could do this in a laboratory. And if we look at the chemical characteristics of crude oil and coal, if you look at coal in particular, you can see stems and roots and leaves and things like that of plants. And if we look closely at the microscopic characteristics of crude oil, we see many biomarkers as well. So what does it take to make an oil accumulation? It's similar to what does it take to make a chocolate chip cookie. You can't have a chocolate chip cookie without chocolate chips and without an oven. Okay, so you can't make an oil accumulation without a pretty rare assembly of things, one after the other, but that's happened enough over time in Earth to make this material in the Earth's surface somewhat common. Okay, so we need a sedimentary basin. And a sedimentary basin, simply stated, is where there is a thicker pile of rocks on the crust than there is in adjacent areas. So for a given interval of time, we had the floor fall out, and we had the opportunity to accumulate a thicker succession of rocks. So if we go up to Wisconsin, it doesn't have a lot of oil because our succession of sedimentary rocks is thin. And if we get into Wisconsin far enough to the north and up into the Ontario part of Canada, there's no sedimentary rocks at all. It's all older basement rocks that are there. So you have to have sedimentary rocks that are a little bit thicker than the surrounding areas. You also need a source rock which is rich in organic material. And these are the black shales. So we have to have conditions at the Earth's surface to accumulate rocks that will produce oil if the rest of the conditions are right. And in the United States, that age of rock happens to be Devonian, which is about 380 or 400 or so million years ago. Okay, so our Devonian strata are those that have the, you've heard of the source rocks like the New Albany in different parts of North America because of our geography and because of our tectonic history during that part of the geologic past, we had the conditions absolutely right for making source rocks. Okay, then after you have the source rock that's rich in organic material, then you got to cook it. You got to take it to just the right depth, which makes it just the right temperature. If it doesn't go deep enough, you're not going to cook it right. You're going to have a raw cookie. If you take it too deep, you're going to burn the cookie, and it's not going to be of any use. Okay, you'll turn it into tar and bubble it away. So you have to cook it. And then you have to have a reservoir rock that will be able, that has the right, and you've seen some of these in the stations today, the right permeability, the right porosity to be able to move it around. Okay, and then you need to be able to move it around so it doesn't leak to the surface. Anybody who's been to the La Brea tar pits knows that oil can reach to the surface on its own if it's not trapped. A lot of the oil that was generated over time, I'm sure, worked its way to the surface and degraded or evaporated. Not all oil is trapped. So we have to have a migration path, and then we have to have a place underground where it's not going to want to migrate up any further. And then we finally get the geologists and geophysicists around to be able to go figure out where it is. Okay, so it's a unique set of characteristics that's common. Now, what we're doing to increase the production nationally now is we aren't worrying about the reservoir rock or the migration path or the trap anymore. This fracking that we just heard about is enabling us to get the oil that hasn't made its way out of the source rock on its own. So we're able to stimulate that source rock by making a bunch of cracks in it to get that oil directly out of there. And that's what we've been doing to make our production increase more than I would have ever guessed 10 years ago. Okay, so where does it start? One of the more important chemical reactions, especially for us, is photosynthesis. So we take carbon dioxide and water vapor and turn it into hydrocarbon, okay, and oxygen. So this is where the building blocks to all these accumulations of oils ultimately starts. So here's an example. Oil is an earth material. This is an asphalt seep in Santa Barbara, California. This is the historic La Brea tar pits and the mastodons or elephants that would have been trapped in there and died. So it's a good paleontological resource. This is a tar sand in Oklahoma. We've seen some things like this in our stations where the pore spaces in the sandstones have so sticky of oil that it just kind of can't move. Okay, you need to stimulate it or heat it up to be able to get it out of there somehow. Okay, and this is an example of one of these Devonian black shales in New York by Watkins Glen. So we have these black source rocks that are ultimately where the hydrocarbon accumulations sit. So the United States, North America in general, has a lot of these source rocks that formed under the right conditions. So, so what do we need? We need high organic productivity. So we need a lot of microscopic organisms to be able to live, and then they have to be able to die and settle to the bottom and not have them rot. Okay, they can't be eaten by a whole lot of other things, and they can't rot. So where do we start? We need shallow waters. So we need ocean waters and shallow waters on a continental interior. Okay, so we need the light for the photosynthesis. Sunlight doesn't penetrate more than 100 or 200 feet in the oceans. So we have to have these things living in the surface areas of the oceans. Has to be at the right temperature. Okay, usually warm shallow waters means that we have higher organic productivity. Let's face it, we like living in warm places more than we like living in cold places if we're life on Earth. Most things are like that. Okay, there has to be nutrients available. There has to be not too much mud in the water, so we can't do it where we have a delta lobe coming in. And we have to have abundant microscopic photosynthesizing algae. We call those phytoplankton. And this is 90% of the organic material in oceans. But we also have fish, we have bacteria, We have small animals as well, but this is where the first building block for oil is. It's these microscopic algae. And these like to grow in shallow, warm, light waters. Okay? Then, these things, as they die, they settle to the bottom with the sediment, which is largely mud. So these black shales have organic carbon in there to begin with. It's not oil yet. It's the first step. It's the raw cookie, if you want to look at it that way. Sometimes it never makes it into the oven. So you have the raw cookie. And what we have in the shallowest burial, say on the order of room temperature, or maybe a little bit warmer than room temperature, a few tens or maybe a little bit more than 100 degrees Fahrenheit, we have some decay and reduction. Okay, so we have bacteria that start modifying these things. We have chemical reduction. These are important. Reduction, oxygen is around, these things rot. Okay, so we have to have it in the bottom of an ocean where you don't have a lot of oxygen. And the way that I like to look at that is some of us have been water skiing in a lake in Wisconsin in the summer. And when we jump out of the boat for the first time, it's warm at the top, but you get down 5 or 6 feet, it's cold really fast. And what you've crossed is what we call a thermocline. And that thermocline sort of is a lid or a barrier between the oxygen-rich waters at the surface and then the black muckety-muck waters at depth don't have that oxygen, so these kind of chemical reactions can occur. Okay, so we start producing methane, carbon dioxide, water, we produce kerogen, more on this in a little bit, and we have sort of a fixed hydrogen to carbon ratio. We really want to get that ratio higher in carbon to be a good hydrocarbon, and the rock undergoes compaction and cementation. You close some of the pores. So when you pile more rock on top of what's already there, or more sediment on top, you lose some of the pores and it gets thinner. So kerogen is this disseminated solid, very microscopic solid organic material in sedimentary rocks. It's insoluble in solvents, and these are some pictures of it so we can see, well, these kind of look like something like algae at one time, and these are the first building block to the oil. So these are organic plant material. These things are more amorphous, hard to tell what it was to begin with, but we can start seeing some of these things in the earliest stages of burial. Okay, so we have this idea that we call the oil window. Okay, or the gas window. So there is a certain range of temperatures, a couple hundred degrees C, and a few kilometers of depth of burial, that is the oven that's necessary to turn it from that chocolate chip cookie dough into the chocolate chip cookie. So if we don't bury the stuff deeply enough, we can't make oil. It remains a black shale, unmature. If we take it too deep, those chemical reactions in the heat break down the more valuable part, the oilier part, and we get a higher concentration of methane. So not all source rocks are able to produce the same kinds of oil. The nice thing about the source rock, the New Albany Shale in the Illinois Basin, is it consistently produced a high quality oil, a valuable oil. Not all oil is equally valuable. If you look at oil prices, you might see something like West Texas Intermediate, which is a light sweet crude like the Illinois Basin. So it depends on how sticky it is, how much sulfur there is how valuable it is. And you can learn more about that tomorrow. So, so how does oil get out of the source rock? And this is a leap of faith that you have to follow the line of reasoning with. So let's say that our source rock, we have 5 or 10% kerogen, or the stuff that can make it into being oil, in these black shales like the New Albany. Okay, so this solid kerogen, as we mature it in this oil window, which is, remember, it is a couple of kilometers in depth, so we make the most oil out of 2 or 3 kilometers in depth and a couple hundred degrees C. If it gets hotter than that, we boil it off into gas. Okay, so when we transform from a solid to a fluid, those of us who teach physics know that fluids have different properties than solids. And one of the more important properties of a fluid is it can't be compressed very easily. And anybody who's ever made a water balloon has noticed this. When you squeeze a water balloon, it squeezes back. So you can't make it, so if you have a round balloon and you squeeze a little bit, it changes shape. Instantaneously. It can't support a shear stress is the fancy way of saying that. So a fluid has different properties. You can't be squeezed any further. So fluids want to squeeze back. So the talk that you just got about hydrofracking, you know, people have been making fractures for decades. Mother Nature has been making hydrofracks forever. So these little bubbles, if you want to think of these as oil, these hydrocarbon fluids, as you squeeze those, they're going to be able to have their own strength and cause the rock to naturally hydrofrack on its own, so they can shoulder aside the rock that's there. That overpressuring of the fluid fractures the rock. Again, this is all natural. This is how you got oil out of the source rock to begin with. Just about every fracture within rock that is natural is a hydrofrack because fluids are present. So you overpressure the fractures in the rocks, the hydrocarbons escape through the microcracks, and then they close as soon as that fluid escapes into the overlying material. So if you have a nice porous unit above that it can move around in, and you have water that is heavier than it, that it can move its way up through, the hydrocarbon leaves. And the next, this happens over and over again as these little bubbles of hydrocarbon are released and formed. And then they kind of form drop by drop into our reservoir. So, a lot of times people think of underground oil as being some sort of a pool, filling up some sort of cave. That's not so. If we look closely at the oil within the rock, sometimes it's not even fully saturated. Sometimes you have migration paths that the fluid can take that are more complicated in geometries. So over time, we're leaking a little bit of this stuff from the source rock. It's migrating up to higher areas. It wants to rise above the water that's there. And if we have a bend in the rock that we call an anticline, it might pile up there a little bit over time until we get a fully saturated reservoir. So the trick is getting it out of the source rock naturally. That's what this hydrofracking that you just heard about is doing artificially. We're helping it get out of the source rock easier. So if we look at North America then, we can see that there are lots of sedimentary basins. And if we compare this to the United States part to the Canada part, Canada is largely too old of rocks to have oil in them. So other continents have rocks that were formed in the wrong environments, rocks that are volcanic, like Japan doesn't have a lick of oil because it's all volcanic in origin. So it depends on your regional geology. So North America, as we'll see, spent most of the Paleozoic era near the equator under shallow water. So we had the opportunity to make these oil-producing situations. So if we look at most of the mid-continent of the North America, from West Texas all the way out to the Appalachian Basin, these basins are all sourced by Devonian rocks. There's some black Cretaceous shales out further to the west. In the Permian Basin, there's some black Permian shales. And in the Gulf Coast, there's some black Cretaceous and tertiary-aged shales. So most of the mid-continent had similar history. The tectonics of North America over time had some parts of crust go up, some parts of crust go down. The ones that went down managed to cook the oil to make the hydrocarbons that we think of today. So a little bit more about the Illinois Basin itself. The colored outline here is the area that is underlain by Pennsylvanian-aged rocks. That's usually how we define the basin. But the thickest rocks are right down here at the corner between Illinois and Indiana and Kentucky. And to make a long story short, during Cambrian time, 550 million years ago, this was a place where a supercontinent like Pangaea during the Permian split apart. And this was an arm to that splitting apart. And this area has been structurally weak ever since. And Pangaea split apart in about the same place too, and some of the seismicity that we have in southern Illinois and Missouri and Tennessee is related to this old plate boundary that happens to be at depth. So this old plate boundary was the floor, and every so often that floor would subside a little bit to pile up these younger and younger sediments. So the Illinois Basin has thousands and thousands of feet of Paleozoic sediments because it was structurally weak, because it was a rift when the Cambrian started. Okay. There's a lot of information in this next diagram. I'm going to show you what the important part is. The time is the horizontal axis, and sea level depth is the vertical axis. So if we look at today, called sea level zero, we can see that for most of the geologic past in North America, if we just look at the red line, we will see that we had shallow seas in North America for much of the last 500 million years. So we had these marine rocks and opportunities to form these black shales. As long as you got the black shales, you can get oil. That's the chocolate chips. Never going to have a chocolate chip cookie without the chocolate chips. Okay, so if you don't have those black shales, you're not going to get an oil accumulation. So we can see that when Pangea was assembled about here, sea level was low, but for most of the Cambrian, Ordovician, Silurian, Devonian, Carboniferous, sea level was a couple hundred meters higher than it is today. So I have some paleogeographic reconstructions that shows what North America looked like during the Paleozoic, and I think it'll be quite clear why we have these oil accumulations here. So here's another newer one. This is a paper that I have in review now. We actually think that this rift actually extends on up into north central Illinois now. So we have some more information on this part of the world now. People would have thought earlier that it maybe just went to here. So this would have been the Cambrian continental margin. We had this basin that extended, or this trough that extended north into where we are now. And underneath Michigan, there's one of these things. Underneath the oil producing areas of Oklahoma and Kansas, there's some more of these things too. So there's these little basins that are at the floor of everything that are pretty important. So you've seen Joan give you a diagram that looks like this. This is all the different layers in Illinois. I'll give you a test on this one in 10 minutes after you have a chance to study it. But what we do know is that the different parts of Illinois, the basement crust is granitic types of rocks, and it's billions of years old. Okay, so we have sands in the bottom of the Cambrian. Those are good aquifers in some places, and they're being really studied a lot as a place to put CO2 for sequestration. So one of the things that the State Survey has been working on for more than a decade now is if we're generating the CO2 from hydrocarbons that we've extracted from the ground, maybe we can inject them somehow back underground as supercritical fluids in the deep Cambrian reservoirs. The Ordovician strata is good for making our roads. So where we have the Ordovician strata exposed in northern Illinois, we got a lot of quarries. The Silurian is good for making roads too, as is the earliest Mississippian. But here's our source rock, that New Albany shale. And the rocks adjacent to the New Albany have the opportunity to be the reservoir rocks. So a lot of the fields that we're going to be looking at tomorrow, I think the 2 or 3 fields that we're going to be looking at tomorrow are going to be reservoir rocks in these Silurian through Mississippian strata. So if we want to look at what North America looked like compared to the other continents, and we can talk at length about how we determine these ancient geographies, but North America spent the period 550 million years ago south of the equator and inverted. So this was the floor where we have our Precambrian rocks, and then if we look towards the end of the Cambrian, we had North America becoming more and more submerged. Okay, so if we look at the part that's now Illinois, we're under one of these shallow seas, where we're getting some sandstones on the beaches, some limestones that are offshore, and we don't really have any mountain building that's happening now. So as we work our way into the later Ordovician, we can see a little bit deeper water in parts of Illinois and Michigan. Maybe some shoals down here in Missouri, but for the most part, we spent the Ordovician underwater. I should have taken those out. And we spent the Silurian, even though a lot of the country became emergent, we're spending the Silurian underwater too, and these are some of the barrier reefs that were being established that are oil bearing in different parts of Illinois. So about the rim up here and around the Michigan Basin too, there are some reef rocks that are good oil reservoirs. As we finally get into the late Devonian, this is the source of the New Albany and all of these other black shale deposits in Texas and Oklahoma and the Williston Basin of North Dakota. We had tectonic activity happening along the Appalachians, and as we get squeezes and mountains building here and there, parts of the interior of the crust subsided to get these black shales. So this is the Devonian time, late Devonian, was the time of deposition of all these black shales. And the reservoir rocks then are generally the rocks that are just above these New Albany shales. There's a variety of sandstones that formed on beaches and barrier islands and river systems that are excellent reservoir rocks. Some of these limestones are good reservoir rocks too, but these sandstones at the top of the Mississippian tend to be among the best. So as we work our way out of the Paleozoic, we see the continent becoming more emergent. The seas are spilling into the edges of what we call North America. And by the time we get into Pennsylvanian time, we just have this little embayment that points towards the Appalachians. And we have lots of coastal coal swamps that were developed at this time here. Some of these Pennsylvanian rocks are also good reservoir rocks. So I just took you through 500 million years in 5 minutes, but one of the other added batches of fun and games here in Illinois is the sedimentation shut off. Really, we don't have very many sedimentary rocks in Illinois except in extreme southern Illinois that are younger than Paleozoic in age, but much of the state has been glaciated, and a lot of the structure and stratigraphy are confined to quarries, they're confined to river valleys, and we have wonderful farmlands because the glacier scraped all the mud from Canada and the southern Great Lakes area and brought it down to where we are now. So I think in a nutshell, that's how Illinois and the United States is blessed with so much oil. It really comes down to this. To me, it comes down to this. We spent the Devonian in the absolute perfect chocolate chip making conditions. Okay, and then things that happened after the Devonian with some of the squeezing that formed Pangea, we developed the structures here that provided wonderful traps for the hydrocarbons, and we brought it deep enough to generate the oil that was available to be generated in those source rocks.